example here, okay? And so what I'm going to prove on this slide is that reversible expansion work is always greater than irreversible expansion work, okay? So how is that so? So let's use, so as an example, isothermal reversible expansion, and I'm going to use for an ideal gas, okay? And here I can call up my equation of state for an ideal gas, right? P is nRT over V. And so for now, we're going to say make N and T constant. So this could be in a closed system where energy is free to exchange but not mass. And isothermal means we're also fixing the temperature, okay? Just for now, to make this an easier example, all right? So now if we know that we have to do, right, work is this equation. Okay, let me take a drink of water. Well, we have an equation for P, right? So we can plug that in. And so that equals negative VI to VF integral. And that's going to be nRT over P. Oops, excuse me. nRT, let me write that a little bit better. nRT over V times dV, okay? Where now we should recognize that N, R, and T are all constants. Because for one, in the scenario, okay, this is another one of these scenarios that I want you to be familiar with, isothermal reversible expansion. In this scenario, N and T are constant. Okay, so that means my integration is pretty straightforward. Negative nRT just times the integral dV over V. Pause the video for a second and just see if you can complete that integral. It's not too bad. You should not even need Mathematica for that one. Okay, see if you can remember how to integrate dV over V. I'm just going to go ahead and give you the answer. It's negative nRT. And then, of course, when I also apply the limits, VF and VI, I get natural log of VF over VI. So recall, the integral dV over V is just natural log of V. Okay? So this is now my equation for calculating work done isothermally and reversibly. Okay, so how is it that reversible expansion is always greater than irreversible expansion? Well, let's go back to this picture I drew, that simplified picture, right? VF over VI, right, where we realize it can go expansion or compression, it doesn't matter. So this area right here represents our irreversible work. Okay, just this shaded area. Oops, I'm not going to do that. I'm just going to say this brown area represents only our irreversible work, okay? Because pressure is fixed. It's only going to be like, along that pressure line, okay? Well, what about the irreversible work? Or excuse me, reversible work, the reversible expansion. Well, here's the equation, PV equals nRT, right? P versus V, Boyle's law, right? It goes like this, okay? And so the reversible work not only contains the area in this yellow part right here, but it also contains the irreversible area as well. It contains both of those areas, okay? Because it has to be the full area under the curve, right? So if I take the whole area under the curve, not only do I have this chunk, but I also have this chunk too, okay? So doing expansion work reversibly not only has the quantity of work that would be if it were irreversible, but it contains an extra quantity needed to ensure that it be reversible. Okay? So it follows that reversible expansion work is always greater than irreversible expansion work. All right? What about a van der Waals gas? Okay? What about it? So I'm not going to do this, but you should try it. And this one is not too bad at all, right? I'll set this up again. We know it's just the simple equation, P dV. But now what does P equal for a van der Waals gas? Well, it's N R T over V minus NB minus A times N over V squared. Okay? So when you put in this value here, right, you're going to integrate this whole expression. It's not so bad, I promise. I'll give you the solution. And the solution is very similar to the solution for an ideal gas. We still have this term, negative nRT natural log, but now instead of it just being simply VF over VI, it's VF minus NB over VI minus NB. And then you have this extra term, minus A N squared 1 over VF times the quantity 1 over VI. And this becomes our isothermal reversible expansion for a van der Waals gas. And now the question is, does it require more work to reversibly expand a van der Waals gas or an ideal gas? Well, that depends on what regime you are in. If you are in the regime where attractive forces dominate, it will be more work to expand a van der Waals gas, right? Because the molecules are being attracted to themselves and you have to pry them apart. However, if you're in a regime where repulsive forces are dominating, where the molecules don't want to get close to each other, it will take less work to reversibly expand a van der Waals gas than an ideal gas. Okay? So it's condition specific, right? Okay. But the important take home is reversible expansion work is always greater than irreversible expansion work because the reversible expansion work contains the area under the curve of irreversible plus its own area for the reversible work as well. Okay? So hopefully that's clear.